Hello, my name is Efe and for the physics project, for our second project of the term, me and my group, we have decided on going with the second problem of the various problems that we were given. And this problem is the one with the two masses inside of a box with springs on either side. And how this problem kind of goes is we have the mass of blue box, I'm going to call it mass blue or mass B, is compressing on a spring on the left side of the box, and the box has a wall on the left side, so the mass is compressing on that spring, and when we let it go, the mass moves, and then they connect with mass red, which is the second block, the red one, and then they move together and hit on the spring on the other side of the box, on the other wall, and we're trying to find how much this spring compresses. And some of the things to note here is that there is no friction, so we're assuming that all energy is conserved. And how we go about solving this problem is, firstly, we need to find the energy of the system, and initially the system is only the mass of the blue block. So we find the energy and we're going to convert it to potential, and then later the system is going to change to both of them together. So the system is going to change from just MB to MB and MR, and then we're going to have to find the momentum when they're together, and afterwards we need to find the kinetic energy when they're moving forward as just one system, and equal it to the spring potential to find the final position of, or delta x, of how much this spring to the right compresses.
All right, I'm Jacob. I'll do the second part with explaining the math. So first, hello, I'm Jacob Hergenrath, and I'll be doing the second part to it. So like FA laid out, we're going to be dealing with a momentum problem with springs and blocks and a lot of potential energies on a frictionless surface. So we're going to first lay out the relevant equations, which is that momentum is equal to mass times velocity, and kinetic energy is equal to 1/2 mass times velocity squared, and the potential spring is equal to 1/2 K constant times the change in x value from its equilibrium point squared. So the first thing we're going to want to do is we're going to find the total energy of the system, which is going to use our potential spring equation, which is 1/2 K times the x initial that it's compressed squared, and we're going to equal that to kinetic energy of the block that it's being compressed by, which is 1/2 mass b times velocity b squared. And we can do that because we can assume that the energy can be transferred from potential to kinetic. And so if we do that, then we could do a little bit of algebra, and this is just an intermediate step, but it's also just showing you some of the math. Is that the K constant x initial squared, we took over the mass B over PB squared, and momentum of V squared is from this equation where we were able to flip some stuff around and get this, and then we're going to isolate that momentum by itself squared and equal that to this, to all the other stuff in the equation, and we get our first equation that we're going to put in somewhere else a little bit later. And then we move on to step number 2, which is we know that from the from the description, that when the blocks hit, they stick together and then move together, so they are now a system. And also, since there's no bounce, we can say that the momentum initial is equal to momentum final. And momentum B, as we learned earlier, is equal to mass B times velocity B. And then we could say that mass R plus mass B is equal to velocity of RB, or of that system together, because we are saying that since no momentum is lost, that both these masses together are now in that system. So we can use this equation, and we can use the fact that since momentum B and momentum of block R and B together are the same, we can start doing some stuff with that, which is finding the total energy of that system now. So the total energy of that system is now going to be equal to 1/2 momentum of RB over velocity RB, which cancels out a V, and we can get this equation where we're going to plug momentum over mass R plus mass B, which again right here we're manipulating this equation around so we can do that. And now we're going to just simplify it a little bit with putting this in. And when we're here, we have something that we recognize, which is momentum RB squared. And since we said earlier that the momentum of RB squared is equal to momentum of B, we can plug in this initial equation and get this equation. So now that we're here, we could go on to step number 3. So we now have this as one system, and now when it hits the other side, we want to see how far it compresses in, which was the initial thing that we were trying to solve for. So we're going to take the potential spring here of the right spring, and which is this equation, 1/2 the K constant times the change from equilibrium squared, which we're specifically looking for. And we're going to equal that to the equation that we just solved for, which was the total energy of the system, or the two blocks together, and we get this. And from here, we just want to simplify it a little bit. We're going to take out the halves, and also the K constants will cancel out. So we can get that the change in equilibrium from x final is equal to x initial, and this times the square root mass B over mass R plus MB. This makes sense because we first had the first step, which is find the energy of this, and then we find, from finding the potential, we find the energy, and then when they collided, we have a new system, found the energy of that, and we could then equate it to this, which got us this.
This is Jules Byer, and I will be going over making logical sense of our answer and breaking it down variable by variable. So we can begin with x initial here, which shows that as x initial increases, the x final increases, and this makes logical sense because the more the left spring is compressed, the more energy it will release as it moves the blue box forward, and will thus compress the right spring further. We can take a look at MB, which is the mass of the blue block, and we can also tell that as that increases, x final increases, which also makes logical sense because the more mass the blue block has, the more force and energy it has that will make it easier to push the red block and compress the spring further. And finally, we can take a look at MR, or the mass of the red block, and that in our equation shows that as MR increases, the x final decreases, and this makes logical sense because the more mass MR has, the harder it will be for the blue block to move it, and it will have less energy and force to compress the final spring. We can relate these to some other physics problems we've done in class, like in both class and studio, we were given examples on whether momentum is conserved or not, and while no specific example matches this problem exactly, those were all really helpful in providing a foundation for knowing how momentum works and whether it's conserved. Another problem that we were given was spring potential energy during one of our Get Ready activities, and it asked us whether spring potential energy is the same when the same spring is compressed or extended the same distance, and the answer to that is yes, the potential energy would be the same, so we also used that logic and reasoning throughout this problem as well. So I hope that explanation was helpful, and thank you for watching our video.